Yeah. So let me make a stopwatch for myself because usually I'm the one who is like watching the schedule, right? So I will be very happy to talk about some of our recent study on how to leverage digital twin and AI to benefit predictive maintenance, right? So as Anne just introduced, so this is now some of the initial results we got from one of our projects funded by the French Research Council, okay? So I will try to be quick and then provide as much as information as I can, but I know we have limited time, so I will cut around 35 minutes so that we have enough time to exchange, right? Okay, so this is the agenda of my talk today. So basically, I'm covering those kind of questions. So first of all, a brief introduction about what is predictive maintenance. So maybe it is a biased understanding from myself, but at least I'm posing the ball, right? We can discuss, right? So, and then we are analyzing what are the gap of predictive maintenance, and then why do we need to consider digital twin and AI, right? And then, so the meat, the beef of this presentation is actually the following two. We are going to introduce one of the open source test platform based on robot, where we develop here for demonstrating how to do predictive maintenance using digital twin. Okay, and then using this, we are showing one very recent study, so which is how we can do system component level for diagnosis using only system level condition monitoring data, right? So it's adding more complexity, of course, with the help of digital twin, right? So let's start. Come on in. So sorry, so I told you that we have this farmer demonstration, so we have people coming in, so in the room. Okay, so what is predictive maintenance, right? So we start with some numbers, right? So this is some numbers telling you in general why maintenance is important, right? So we are losing a lot of money for not doing maintenance properly, right? And if you are looking at the literature, so this slide basically summarizes the existing maintenance strategy, right? So Professor Barros talked about condition-based maintenance, but you can see there's many. And then among them, so predictive maintenance is, I would say, the most up-to-date one. So what does this mean? So basically, this graph kind of summarizes what do I understand as predictive maintenance. So everything starts from sensors deployed in your physical system, and then the sensors will feed you real-time or like approximately real-time condition monitoring data from your sensor, for example, like voltage, position, temperature, okay? And then using those kind of condition monitoring data, we are developing models, right? So predictive models. And those models, so it's targeting at three main important questions, right? Fault detection, diagnosis, and prognosis. So those are the three main essential tasks people usually consider in predictive maintenance, right? So what are they? So detection, so it's basically we have data up to today, and then the answer we want to answer is basically, the question we want to answer is, based on the data you have, so at the current moment, is your model working well or not well, right? So then in general, the approach is like this. So we have some historical data, and using that, we can construct a model that predict if everything is fine. So then what should be the reference signal? And then you compare your measurement with this reference, create residue, and then you make your decision based on the residue value, right? And then diagnosis, so it's a problem. Basically, we observe this. We have some failure at the current moment, and we want to understand why. So why this failure happens. So on which component, which failure mode, right? So typically, basically, we treat that as kind of multi-class classification problem. So this is an example we did before. So basically, we have a four state of bearing. We collect bearing data, and then we try to develop a deep learning model to tell which model it is. So this is diagnosis, right? And then lastly, we have prognostics. So what is prognostics? So we're not just limit ourselves for what's happening now. We are predicting what is going to happen in the future. So prediction of remaining useful life, and then not just predicting remaining useful life, we want to plan maintenance activity, right? So this is a very nice work we did with Miela. So I think she's going to talk about this maybe in the afternoon in details. But anyway, so we make prediction about remaining useful life, and we try to plan what should you want, given this IO prediction, what would you like to do, right? For the component, but also for a large scale system, we have this maintenance schedule, okay? So a very quick summary. So what is predictive maintenance? So basically we have condition monitoring data, from sensor, okay? And then we want to do these 3 basic tasks: detection, diagnosis, and IO prediction, and then maintenance planning, right? So this is what do we have for today, right? But then why do we need digital twin, right? So if you look at the current literature, so the state of our approach of for predictive maintenance is more and more transition to data-driven. So basically, you train a deep learning model, you throw data to that, you train the model. So as soon as you have abundance of training data, usually the model performs good, right? But then the major limitation is that you need to have a really huge amount of training data, and those data should be failure data in order to train your deep learning model well. But failure data is really very, very rare, in reality, because you don't want to see failure happen every day, right? So then this is kind of like a paradox, right? So in order to train your model, you need failure data. But if your model is really good, then you need to avoid failure. Then you don't have failure data. Right? How to solve this problem? So this is the starting point of our research and why digital twin comes in. Okay. So then before I explain how we are going to use digital twin, so let's spend a few minutes just to discuss what is digital twin, right? So I think everybody's talking about digital twin, but maybe 1,000 reader might have 1,000 digital twin definition, right? So if you go back to the origin, so this is the original definition of digital twin. So roughly speaking, you can consider that you have in the virtual space, you have a virtual copy of your physical entity, and then this one can simulate very accurately what's going on here, and then you have data information flow constantly, in bi-direction between the virtual space and physical space, right? So this is more or less people will agree. So here, so if you want really to check the definition, so it's really 1,000 definition in the literature, but more or less they will agree on what I talked before, right? But then here's a key question, right? So then why do we call it a digital twin? So isn't that just a simulation model? So how can we distinguish a digital twin from a simulation model like, Simulink or like a finite element analysis, right? So then I think in the digital twin community, most of people will accept these 3 levels of classification. So we have a digital model, digital shadow, and then digital twin, right? So in the digital shadow, so in the digital model level, so it's kind of like the conventional simulation model we are doing, right? So we are running the simulation, and then in this graph, so then basically the simulation is usually running, sorry. So sorry, so people is still coming. So the simulation is running offline, and then you see here, so you have the lines dashed. So then basically your model is static, and the model does not exchange, data and information with the physical quantity. So this is a digital model level. And then if you move one layer above, so you have this digital shadow. So that means you see here, so the data flow from the physical entity to the digital space becomes solid. So then basically your digital model is taking data from the reality so that whatever happens in reality, so your model will capture that, right? But the data flow from digital space to the physical space is still dashed. So you're not using your model to make decision and then control your physical quantity. So this is digital shadow. And then when it comes to the digital twin, so we need to have this kind of bi-directional flow. So your model is updating itself using what you observe. But what's more, your model is trying to make some decision, right? So what is your decision problem? And then using those kind of decision you take in real time and then send control signal and information back to the physical space, right? So this is a digital twin, okay? So the 3 levels. So then what we want to benefit from, benefit predictive maintenance from digital twin is actually, so we want to solve the problem of lacking failure data, right? And then a very naive and straightforward way, if you are lacking failure data and then you have a digital twin that can simulate the behavior quite accurately, then why not using your digital twin to generate some failure data and then train your model in the virtual space and then just try to apply that in reality, right? So this is the starting point of this research, okay? So, but to do this, we need to have a solid, physical system first, and then the digital twin, and then we do all the stuff, right? Because otherwise, it's in Chinese we say, 纸上得来终觉浅，觉知此事要躬行. So you cannot do really good research if you don't have a solid stuff to try, Otherwise it's just equations on the papers. So that's why we are developing this robot demonstrator. Okay, so everything is right now, so it's not complete, but we already put everything we have on the GitHub repository, so you can access if you want. Everything is open. So the goal, so the ultimate goal is actually to build a mini production line, a mini factory like this. So you can see you have a warehouse area here, and then you have some conveyor, okay, robot for doing the operation, and then we have AGV for transferring goods from the warehouse area and then to the manufacturing area. And then the goods we are manufacturing is these toys, okay, because I have a son for 4 years, right? So 4 years old. So if you want to support, ask him to support my research. By support, I mean just stop crying when I was, doing research. Then you need to have this kind of charming project for kids, okay? So the customer will choose which kind of toy you want, okay? And then we pick up the raw materials here, use the AGV to move it here, and then we do the assembly here, and then the final product will be delivered here, okay? And then this is the idea, okay? And then what we want to do is not just to have this factory running. We want to have the digital twin of this factory, okay? And this digital twin of the factory will build, so first of all, on the digital twin of the robot, AGV, okay? And then maybe also the operation model on the factory level, right? And then, so we are using this those digital twin model for the robot and the factory, try to do predictive maintenance, right? So this is the general idea, okay? So this is a quite ambitious goal. So we are still, working day and night on that. So right now, by the way, so we designed this factory based on the real factory. So this is a factory in France, in southern France, near Lyon. So where we visit. So basically, we designed this, the layout based on this factory. Oh, sorry. And so so it's an ambitious project. So right now on the plant level, so it's still under development. But on the robot level, so we are already quite confident to have some solid result to show, right? So this slide just shows a very quick demo of what we achieved in terms of digital twin modeling of the robot. So you can see we have the digital model here, which can simulate the behavior of the robot. So in the nominal case, without failure, and then we can also inject failure in the robot, so on the right, okay? And we also have this condition monitoring system. So for each robot, it's driven by 6 motors. So, and then we can collect in real time, so the position, temperature, and then voltage for each one of the 6 motors, okay? So it's a condition monitoring signal. We can use that to do predictive maintenance, okay? And then it's a digital, you can see here, so it's a digital shadow. So basically, whatever is happening in the physical space, basically your virtual model get that and then update itself, right? So this is what we achieved so far, right? And then what we are trying to do now is actually working on the decision problem, right? So we are considering actually 2 decision problems. One is actually fault detection and diagnosis, and then the second one, which is even more interesting, is how to adapt your robot. So if you detect you have a failure, so the original control algorithm might not be valid. So then is it possible to revise your control algorithm in real time so that you can compensate, those kind of failure? So this is what we are trying to do, okay? But today, what I can show you, so here are some technical details. I just skip that. So today, what I would like to really discuss with you is, one of the use case we did on the fault diagnosis part, right? So this is a study we did with 2 master students here. So through a very good, project, okay? So the idea, what we want to do here is actually we want to do a component level diagnosis, okay? So on this robot, we have 4 motor. We want to diagnose for what's happening on the motor level. But the data we can use is only the system level condition monitoring. So basically, we only observe the movement of the end effector, but not what's happening. What's happening on the component level. We observe what's happening on the system level, and we try to infer, which failure is happening on the component level, right? So for diagnosis, I think it's an interesting use case because very often it's very difficult to deploy sensor on the component level. Sometimes we have to observe, system level, monitoring signal, and then we try to do this kind of inference, right? So then what is our system level monitoring? So basically, we are considering the movement of the gripper. Okay, and then basically we have this kind of sensor. So it's a accelerometer. So you can put this accelerometer on the gripper, and then so it's a demo here. So the robot move, and then you can just collect the acceleration, doing double integration. Then you can reconstruct what's going on here. So basically, what we observe is the movement trajectory of the gripper, and then we want to infer from the movement of the trajectory what's happening on the motor level. So which motor is in failure state, and then in which one, right? So this is the final goal, the ultimate goal, right? So basically, we are considering 4 motors. So 1, 2, 3, 4, right? Because only the 4 motor have some impact on the trajectory of the gripper, okay? And then for each motor, basically there are 3 possible states. So nominal state, so normal, no failure. And then we have 2 failure mode that is considered simulated. One is motor stuck, so it gets stuck, cannot move. And then the other is steady state error. So you send a control command 30 degree, and then so it has a steady state error, so maybe 20%. So, but in general, it's larger than the data sheet requirement. Okay. So then in total, we have 4 motor, and then each one have 3 state. So basically, for the altogether, we have 9 state, right? So once everything is fine, and then so 2 failure mode for each one of the 4 motors. So 8 failure states, altogether 9 states, right? And then what we observe is the XY coordinate trajectory of the gripper here, right? So then the general idea is actually we try to use this digital twin model. Okay, so basically you give control command for each motor, but you don't observe the response of the motor, but rather, so you observe, the trajectory, right? So maybe for the rubber use case, it sounds a little bit dumb, right? So why don't you directly observe the response of the motor? But we just want to demonstrate, so we can do that, right? Okay, and then, so the 2 failure modes. So this is a steady state error. So you have some constant error, right, on the motor level, and then if you get stuck, it just stop here, right? So then the workflow is like this. So basically, we generate using this digital twin model. So 400 random trajectory per class. Okay, so then altogether it's 3,600 trajectory. Okay, so it's a random movement like this. So each trajectory is 10 seconds, and then it's divided by 5 segments. So basically, you just repeat 5 movements. Okay, and for each movement, you just send a signal to ramp up to a certain degree and then hold there. Okay, so you can see like this. Okay, and then so for each data trajectory, so each data set, so it's a 10 second, but the sampling rate is 100 hertz. So you have it's a time series of 1,000 points. So 3,600 sequence like this. Okay, and then we train a AI model to do the full diagnosis using those data here, okay? And then when we are testing, so basically we move to the real robot because we have this real robot. So we do the same experiment in the real robot, and then because it's real robot, it takes some time. So then basically we collect only 10 trajectory per class. So altogether it's 90. It's 90, testing data set, right? So the features, basically we have the control command on the motor level, okay? And then the trajectory response of the end effector, right? So this is all the data set. So the data set right now is already on the GitHub. So if you want to reproduce what we did and try to, beat us, so please, okay? And then, so here is a demo, right? So just to show you briefly, so what does the trajectory look like, and then have some kind of, so I need to, just give me one moment. So, yeah, so this is what we mean by a random trajectory, so like this. So what we observe is just like the movement of the gripper, right? And then, so there are 2 cases, right? So one is for stack, right? One is for steady state error, right? So basically, I hide, the legend, on purpose, just to let you guess, right? So which one do you think is the nominal case without failure, and which one do you think is the failure case, right? So let me just play. Yeah, right. So can you distinguish just by eyes? Let me just play, right? What do you think, right? It's difficult, right? So it's difficult. So even for a human, it's kind of like difficult. But at least I think for this one, it's kind of apparent because apparently this motor block, right? It doesn't move, right? But for these two, so the steady state error compared to the nominal case is a little bit difficult, right? So for a human, right? So actually, so then for human beings, it might be challenging, but let's see if we can achieve better result by designing an AI-based approach, right? So this is what I'm trying to do. So how can we do that? Okay, so the idea is basically just to train a AI model using the simulation data, right? So then the model we trained is actually a deep, not too deep, okay? So I would say a shallow LSTM. So because it got only 2 LSTM layer, okay, and then a fully connected layer, and then it's just like a softmax layer for classification. So then what we designed experiment is basically like this. So we first split the training data set 90 to 10. Training and validation. So we use the validation data set to tune some parameters in the training, okay? And then we just apply the trend data on the real data set we have, right? And so I think everybody knows that if you are training any kind of AI algorithm, there are some kind of randomness. So we repeat the result 5 times to account for the randomness in terms of training. Okay, so then this is the result, right? So we have some interesting result to show, right? So this is the first one, right? So we have 2 ways of building the model. So one is actually we use the original feature, right? So the original feature is actually we only observe on the system level, right? We have this control command to the motor, and then the response on the gripper, okay? So this is the original feature. And then the second way is actually we have the digital twin model. So we try to use the digital twin model to augment, the original feature, to try to get some additional feature. So what we do is actually we use the control command, put that into the digital twin model so that you can get a desired response of the undefected gripper. And then you can calculate the residue, right? So we use the residue to train the model, right? If you compare these 2 ways, so actually you can see the final performance is kind of the same, but if you are using digital twin to augment the feature, actually your model will converge faster. Okay, so this is a very good indication. So basically, if you are using digital twin to generate a new feature, then actually it kind of help you to solve this kind of it's kind of like giving you additional input, right? So that the model can be learning faster, right? So this is the one interesting stuff. And then the second one is actually even more interesting to discuss, right? So this table summarizes the performance on the training data set, validation data set, and the test data set. Okay, so validation set. So it's also from the simulation data. We'll just do a random split, right? So you can see actually the model trend on the simulation data set, if it is applied on the simulation data set, actually the performance is quite good. Okay, so the accuracy can go to 90%. But if you apply to the real data, real robot, then you have a dramatic drop of the performance. Right now, we can only got 60%, right? And then if you see the performance on each class, actually you can see for the healthy class, it's very bad. So it's NAN because basically it makes no correct prediction. So it kind of like misclassify all the healthy cases, okay? And why do we have this, okay? So in this graph, actually, we did a small experiment. So we take one testing data, and then we use the digital twin model to simulate the same trajectory, and then we see if the simulation from the digital twin actually match the real data, right? So you can see this graph shows the residue. So the blue curve is the digital twin simulation, and then the black curve is the real data. So you can see actually the digital twin model the simulation, we wouldn't say it's not accurate. It's actually accurate, but it's just like in the real robot, we have larger noise. Okay, so we have a larger noise, and then that makes your model basically doesn't work well because your simulation model cannot fully capture the real behavior because of the noise, not because of the nominal behavior, right? So how to solve the problem, right? So this is the issue. And if you're talking about AI, if we're using the AI terminology, so the result of this is basically you have a large discrepancy between your training data and testing data, or your source domain. If you're using the language of transfer learning, so your source domain and your target domain is actually quite different, right? So how can we solve this issue? So so we did quite a lot of initial study. So first, let's start by some failures, right? So something that does not work, right? So one very straightforward idea is that if we are having noise, right? So if the real data have larger noise, then why not generate noise, right, in your training data set? But if you directly add random noise, a Gaussian white noise, so basically it doesn't work. Okay, so it doesn't work. And why it doesn't work is because basically it's not random noise, but actually the noise have some kind of pattern, because actually our data set have 5 movement, right? You can see here the noise have some behavior dependent on, it's from which particular movement, right? So if you directly generate a purely random noise, it doesn't work, right? And what is even more surprising is actually we try transfer learning. So meaning that we just freeze, all the layers before the last layer, and then we just tune the last layer with the real data. So usually transfer learning should be working, right? Because in theory, so your previous layer can learn some, deep feature, and then it can be applied well. But if we just do a simple transfer learning, fix all the layers, n-1, and then only tune the last layer, actually it doesn't work as well, right? And then my interpretation is that although the previous layers can learn a little bit the features, but the features are still different from the reality, right? So that's why maybe it does not generalize well, right? Then up to now, so the best approach we have is to add a module in the digital twin model, and this module will simulate the noise. So meaning that for each segment, so it generates the noise, and it's generated by adding a command to the motor. So then maybe it takes a short time to react, right? And then, of course, you have some parameters to tune. For example, what is the lower bound and upper bound of your steady state error, and then what is the delay time for your, delay, okay? So to tune those kind of parameters, so we treat that as a hyperparameter, and then we collect a few real data so that we can update this digital twin model, and then just like a hyperparameter tuning, right? And then we retrain the model using the updated digital twin model, right? So if we do this, okay, so so you can see the comparison. So this is the original result, right? And then this is the result we got from the new model. So sorry, the format is not very clean, but because it's very recent, right? So you can see if you're adding noise, actually when you are training your model, so the accuracy drop, okay? On the validation set, the accuracy also drop. Okay, but on the testing data set, it's actually improved. And then the performance between your validation set and then the test set is closer, which is a good sign, because basically your model is not overfitting a lot, and then it's actually aligned with more aligned with the reality, right? So this is a very recent result, but we are still trying to improve that. But at least this is the approach we have so far, right? So I think I don't have too much time, so I'm going to wrap up. Okay, so for this study, there are a few key takeaways, right? So what do we do? What we are trying to do is actually we are trying to solve a problem how to make component level diagnosis using only system level condition monitoring. And then the way we are doing that is actually we are trying to leverage digital twin to learn some additional feature and then to train the model, right? So the main finding is that actually if you use your digital twin to augment features, actually it can help you to solve this problem, because actually it's providing additional input, right? But the key challenge for in general, I think using digital twin to support predictive maintenance is this one, right? So the reality is usually not as perfect as you model, right? Because if you're developing a digital twin model, even though we do calibration tests, right? But the calibration test is kind of still performed in kind of like controlled environment, right? But if you really deploy your model in industrial case or practical case, then you might have noise. So the data is much more noisy. So how to kind of like compensate for the noisy reality from an algorithm perspective. So I think this is the challenging work, right? So on this direction, so we have some students working on this as well. So we are trying to further improve the performance by further align, our virtual space with the reality. So here are a few ideas that we are trying, right? So on this work, so although we didn't submit a journal paper yet, but we do have one, preprint in archive, and then everything is in GitHub. So the data set, including the data set, and then the digital twin model, so everything is there. So if you are interested, so you are more than welcome to try. And then if you discover some, something to improve, just let me know. Okay, so I will be more than happy to realize that someone achieved better result than us. Okay, so summary and our thoughts, right? So then our vision, okay, so not just for this ANEC project, but in general, so our vision is basically we want to really have this kind of open source demonstrator, not just on the robot, but on the whole plant, so that we can demonstrate a lot of research ideas, right? So the predictive maintenance, even how to integrate maintenance with production scheduling. So all those kind of good ideas, right? And then we really want to develop and talk about digital failure twin, right? So I didn't formally introduce this concept yet, right? So my idea is that if you're talking about digital twin, so although you see people are using that to do failure simulation, but those digital twins are designed for simulating normal behaviors, right? So what we really want to do is actually we're asking ourselves a question: if we want to develop a digital twin to simulate all the possible failures of your system, what kind of digital twin model we should use, right? Is it you just copy the same structure, or do you need to have some kind of new architecture, right? So this is what we have right now, right? So you need to have your digital twin model simulating your normal behavior. Then you need to have your failure behavior model. That means you need to first understand for your system what kind of failure is going to happen, right? And then how to model that. That's already require a lot of knowledge engineering, database, and then how to simulate that. And then integrate everything together in order to solve decision problem, right? So maybe it's very small here, right? So we are trying to consider different kind of decision problems. So diagnosis is one, certainly, but we are also considering other decision problem like fault tolerant control, for example. If you diagnose that your motor one block, is it possible to compensate that from the control algorithm perspective? Right? You can still reach your final destination. Just do not use motor number one. Right? So how to do that, right? And then so I think Christopher is going to talk about IOL driven control. So this is also something we want to try, right? So one trajectory of a robot, you have a 4 motor. And then right now, if you look at the trajectory planning algorithm, so basically you have an objective function, which is minimizing energy consumption, right? And people do not consider actually the different motor might have different degradation level, right? So then if we consider that, so it's actually a good added value. So then basically you can make you robot, running longer, right? So a lot of nice idea here, but in general, we want to really have a digital twin to benefit our field, right? So finally, I always try to make some fun story from traditional Chinese culture, right? So this is actually a very famous story called the 扁鹊见蔡桓公. So I think every Chinese people know about that. So in ancient times, there's a famous doctor called Dr. 扁鹊, and then there's a king, and then one day, so this Mr. Bianche visits this king saying, "Oh, so Mister, so you have some diseases, maybe in your skins, right? And then if I do not intervene, if I don't do predictive maintenance right now, so it's going to get worse, okay? But the king says, but I feel okay. So you are a liar, so you just try to, earn some money, okay? So then he left. And then 30 days later, he come back. Oh, so your disease gets worse, right? So if I do not treat you right now, then it's going to be even worse, right? So no response, I'm okay. So 30 days later, so the doctor visit the king again. The moment he see the king, he run away because the disease is already so severe, right? So he's going to die, many times, in about 1 or 2 weeks, and then he dies, right? So then this story tells us, it's always better to do predictive maintenance. But the thing is that in the ancient times, so they are not doing continuous condition monitoring, right? So it's like 30 days, then it's already too late, right? So our vision is actually really benefit robot machines, right? So this is actually a recent news that people are starting teaching robots to repair themselves, right? So it's a group of Japanese people. So they are actually teaching the robot to tighten the screws, okay? But up to now, the robot know only how to tighten the screw. You still need to tell him which screw you need to tighten. Okay, but our vision is actually to leverage all these kind of algorithm to really let the robot to know when to repair and then how to repair. Right. So so I skip this one. Okay. Yeah. So we are living in a area now. We are having more and more interconnection, adding up complexity, which is creating a lot of issues, right, in terms of reliability and then maintenance, right? But again, so I don't know if you know, in Chinese actually, so crisis and opportunity is one word. Okay, we say that Weizi, which integrate crisis and opportunity. Whenever you have crisis, there is opportunity. So that means, although we are facing new challenge in terms of this new error, in terms of reliability, as long as we can find the correct solution, actually we have better opportunity to improve. And for me, the correct solution for predictive maintenance in this new era is actually leveraging digital twin and AI. So I really would like you to work together, okay, so that together we can make a more reliable world, okay? So with this, I think I can close my section, and then hopefully we can have some minute left to discussion and questions. Okay, thank you very much. So any questions? On site or online? So I will be happy to take questions. Yeah, yeah.
The noise generated, the noise in this physical system.
Yes.
Robot, you mentioned that goes in noise. Could you try to characterize the nature of that noise and have this?
Yes. Okay, I just repeat the questions for people online. So Pierre, so it's Pierre Desson from, right now you are with yeah, so Luther University, so from Sweden. So the question is basically, I mentioned that we have some specific pattern in terms of the noise, and it's not Gaussian. And his suggestion is, can we try to characterize, which pattern, and then maybe model that sarcastically, maybe, right? So the answer is definitely. So I think it's a very good suggestion, and we are trying to do this. And then the thing is that I'm still not sure if we should model that as maybe a stochastic process. So this is one way, right? And then maybe a probability distribution, or we are also trying another idea, which is actually we are training a machine learning model to predict this kind of noise. So both are trying, but I cannot tell you at the current moment which one is working. But I think it's a very good suggestion. Okay. I saw there's a question online, and so it's a comment. Okay. Never waste a good crisis. Yeah. So it seems that Winston Churchill know Chinese. Huh? I never know about that, but it seems that okay, pretty well. Yeah. Other question? Yeah, Giovanni, please. Yeah.
Thank you, Zhiguo. Very nice presentation. I was wondering how transferable is this in an industrial practice?
Yes.
How do you see the transferable to other types of situations, like
Yeah.
with multiple robots?
Yes.
With maybe let's say your sources of noise can also not be motors.
Yes.
Necessarily, right?
Yes.
So
yes. Yes. Yes.
How do you see this?
So yeah. So again, I repeat the question. So it's from Giovanni, so one of our speakers. So his question is mainly about if we are considering maybe a real industrial case, maybe we have multiple robots, and then how do we expect if this approach can be transferred, to this real setting? So I would say that is why we are trying to develop this mini plant, right? So then we have this kind of a multi-robot setting, right? And then we do consider trying maybe in the next step, which is actually we train a model on one robot, right? And then we try to transfer that to the other robot. Maybe it requires some kind of fine tuning, right? This is something we have in mind. But on the other hand, I also have to admit that although this is already a simulation plan, but I think it's still far away from the industrial practice. So in industrial practice, first of all, you have a larger robot, and then maybe the protocol is different. Then I cannot answer. So I think I need to have a project with an industrial partner, right? But I think at least right now, so in terms of theory, so I think it's there, right? But applying the theory to a reality, sometimes it requires a lot of effort. So yeah, but if you have some project, we can work together. Yeah. Okay. So there's one question online. So I do a pretty in railway freight wagon. Well, okay. Should we do some for diagnosis of wheel set using digital twin? This is a question. But if I see the test like this, I can only answer yes, of course, right? But then the thing is that it depends on your real case, right? So for example, if you are really want to apply in digital twin, then is it possible to develop digital twin in the first place, right? So in the case of robot, actually we spend quite a lot of time to really have the digital twin done. Right? And then I think in your case, if this wheel set, maybe you are more concerned about mechanical stress, then maybe you need some finite element model. So then I think Konstantinos will talk about this maybe later. But in general, so I think it's highly case dependent, right? You need to make sure that first of all you have the digital twin, and then maybe start with some initial study just to see how plausible it is. Okay. So I think if we don't have question, then another one, yeah.
Thank you for the interesting presentation.
Yes.
I have a little bit small question about when you add the noise to the training data.
Yeah.
So as you know, it's optimal, and for example, with the other solution, because as I know, we can also add the noise during the training.
Like GA and GAM for them. Yeah.
When you apply, for example, calendars,
yes.
we can apply the noise.
Yes. Yes.
And we can control the optimal
yes.
level of
yeah.
noise.
Yeah.
What we compare and how.
Yes. So yeah, again, I repeat the question. The question is actually when we are adding the noise here, so it seems that it's quite simple and naive, right? So then how can we make sure that, it's the optimal degree of noise adding? And then maybe there's another comment is actually we have some algorithm, right? So for example, even some architecture like generative adversary network or something like this. So can we consider like doing some study, like benchmark a little bit? So a quick answer is actually here we cannot ensure it's optimal. Because we are everything is still like ongoing. So this is just like the initial result we get, and we're just getting a result that is working. So right now we cannot ensure it's optimal. But in this study, basically what we are doing is actually we are doing kind of like hyperparameter tuning. So we have some parameter in this noise module, which is actually tuned from the test data. But I agree. So we should definitely try to see other algorithm or other architecture, and then maybe we are going to. So maybe this one will become very soon outdated, and then we are going to have better algorithm. Thank you. Yeah, thank you for the comment.
Okay. Thank you, Professor Zeng.
Yeah, thank you. Yeah.